which for some will need little explanation or justification, perhaps the original stage. But elsewhere, they're making very deep skepticism about the role of science in society. Have you really had enough of experts? Haven't scientists been shown to be wrong about all manner of things? And why should we believe them about climate change? If you dip into Twitter, you'll see people arguing about this all the time, and it can get pretty ugly. Now, it would be wrong of me to call some of these people idiots. And next week, one of them becomes the 45th president of the United States. But I would say now more than ever that we need climate scientists to effectively engage beyond their disciplines, to be strong advocates for science and its importance to life society. So to that end, I can't think of anyone better qualified than our guest speaker this evening. This is where I pick up. So he studied mathematics at Oxford as an undergraduate. Then he did his PhD at the University College London. His research took him to the United States of America and eventually NASA's Goddard Institute for Space Studies. In 2014, he was appointed as the director of the institute to take over the role from Jim Hansen. Hansen, who's done more perhaps than any other climate scientist in raising the profile of climate change in both public policy and the general public arenas. Now, our speaker this evening has certainly continued such work. As well as being an internationally renowned scientist, he's championed communication of science by working with organizations such as the American Museum of Natural History and the New York Academy of Sciences on science and education outreach projects. He was the co-founder of the Real Climate blog, which provides critical commentary on climate science and has grown to be an invaluable resource for the public and journalists. He's made many media appearances, including The Late Show with David Letterman, The Daily Show with Jon Stewart, and his 2014 TED Talk on climate change has been viewed over 1 million times. In recognition of these and many other activities, in 2011, the American Geophysical Union awarded him the inaugural Climate Communications Prize. So we are extremely fortunate to have him speak to us tonight and explain what is climate science good for. Please give a very warm welcome to Dr. Gavin Schmidt.
I'm very happy to be here. I'm very glad. I had some great conversations today with all manner of people who are working at the university here. And I'm going to talk to you a little bit about why we do what we do. What is it actually good for? All of the academic researching, talking, discussing and talking again. There's a lot of talking. And I'm going to try and convince you that it is good for something. And if I fail, then I'll be upset. So be polite when I get to the end. So even if you're not totally convinced, cap anyone, I'll appreciate it. I was just finishing up this talk, global over there. Can you not hear me? Is that what you're ready?
Turn it up, please.
Turn it up. It's called bladder. Right, do I need to hang out over here? Can you hear me now? Yes. Okay, yes, I shall stand over here and try not to. I always have a tendency to wander. So that's why I ended up in the States, of course. So I was working away, putting some finishing touches to my masterpiece presentation, as one does, because it's never really right, it's never really finished, a bit like modeling. And my computer crashed, and everything that I've done today actually just disappeared. Well, not only it disappeared, what I've been working on, it also disappeared. So the file that had been there that I was using as my template, that disappeared. And so with about 25 minutes before I'm supposed to start here, I had to start all over again. And so this is not quite the presentation that I was going to do, but it's not too bad. And it's quite close to where I was going. But I thought I'd just share the fact that if this ever happens to you, and it might, always have backups on a spare stick. So that you can back up things. So no notice. You have a little domino panic there when everything disappears and you're about to be on stage in half an hour. It's not good. So let me get to the actual point of this talk. What is climate science good for? Is it good just for simulations of nice pictures? So you know what you're seeing here? This is water vapor. Imagine a total amount of water vapor in the atmosphere in a simulation of the climate. And you can see there's a lot of water vapor in the tropics, as you might expect. There's not so much in the high latitudes. But you see these great swirling patterns with storms and atmospheric rivers. And you can see a couple of typhoons kind of meandering around. Maybe I was just about to start off. Well, there's two of them, yes. Things that you might actually see in the real world in this simulation. None of those things that I was pointed out, the swirliness, the typhoons, the fact that the tropics are wetter in the poles, none of those things are embedded within the country. They're all emergent properties of all of the different small-scale processes that we kind of synergize and synthesize within the simulations. So, climate change. Well, we know that climate has changed. Right? You can see things like this. This is a photograph of the glacier of Alaska, taken in 1884. We can go to that exact same spot now and see what it looks like. Compare those two things again. Oh, this is too exciting. Okay. The glacier has receded kilometers. And we can go pretty much anywhere in the world and we will see the same kind of impact on mountain glaciers. Whether it's in the Alps, in the Himalayas, in Papua New Guinea. Most people don't know that there are glaciers in Papua New Guinea, or there really aren't anymore. And you can see that things have changed. We can go to places like Baffin Island, where there are ice caps that are slowly receding, and they're such interesting places that the turf and the mosses that were there when it first snowed and ended in melt are still there, preserved in a deep freeze for many thousands of years. And we can go back and we can date those mosses, and we can date the grass that's grown there, and we can ask, well, how old is this grass? How old is this moss? And we can use the radiocarbon clock, which allows us to date things back to 50,000 years or so. And we can go back to these places and we can find areas that have not been uncovered for more than 1,000 years, sometimes for more than 4,000 years. And in fact, for this particular case, the turf and the stuff that we're measuring is so old that there's no radiocarbon in it at all, which means that it's effectively older than 15,000 years old. And so the receding of this particular ice cap is something that is unique on perhaps 120,000 year timescale. Things are changing. So climate science is really focused on 4 questions. How has the climate changed in the past? Because we know that it has, but what's the synthesis of all of these different things? Why does it change at all? What are the drivers of climate change? How do we know that these things actually are? And how might it change in the future? And of course, what will the impact? So these are the kind of 4 primary questions that we have. The first one is really a function of the people who are out there in the field taking icicles, taking ocean sediment cores, tree rings, looking at the geology and piecing it together. It's an observational science combined with perhaps a statistical modeling approach to kind of put things together in a way that's coherent. But you need models as well to try and interpret why the climate changes is clearly a modeling question. You need a model to be able to determine if I change this variable, or change that variable, what are the consequences of these things going to be? We know how complicated climate is, and so you can't just do that in your head. You have to use a model that includes much, much more of detail. And of course, if you're going to go into the future, you have no observations of the future, and so you're going to need a model for that. The impacts of change, whether climate change is driven by any natural phenomena or things that we are doing as humans, those things also need models that take those changes and project them down onto the systems, the locations, the vulnerabilities that we have as a society or ecosystems. So I'm going to try and give you a little bit of a flavor of how this works. So this is what the climate has been changing in that same period as the two glacier photographs that I showed you. Right, but this is much more complicated, right? There's ups and downs, and there's wiggles, and there's red dots, and there's black dots, and red lines, and numbers that seem to be quite quantitative but quite small. And so what's going on here? Is this a laser function? It's a laser function. It's not. So what have we got that's going on here? Right? So basically each of those dots is a single year, and it's an estimate of how warm that year was relative to the year. Right, what I've done here is I've baselined it to the 19th century. So all of the numbers are how much warmer it is since the late 19th century. And so that blue line there, that's 1 degree above the late 19th century. We can see that back in 2015, back in 2015, which is the last dot we had there, we approached that 1 degree level for the first time. Okay. 2016 is, oddly enough, will be announced to be a record warm year next year. It's heavy, something most of everyone knows, because we have 11 out of 12 months already, so we can make a pretty good estimate of what 2016 annual number will be. What you can see is that the trends go up and down a little bit as a function of time. The short-term trends can be very busy, but overall we have a warming climate, and it's getting warmer and warmer. It's not going to be a record year every year. Next year will be a little bit cooler, but it will still be quite warm. And it will be a continuation of that long-term trend. But let's be clear here, right? Does 1 degree seem like a lot? Does 1 degree seem like a lot? That's a bit of an introduction.
No.
No. Yeah. Yes. Come on, too bad. No. Yes. Well, it's hard to know. Right. And I sense your hesitation. Because in a lot of circumstances, when degrees number, the temperature in this room here will go up a couple of degrees because we're all sitting here emitting about 100 watts out of the top of our heads as we do so, warming up this quite appallingly heated environment that we reach from. I live in America now, environments. I find it very difficult. Even in summer. So is it a big number, or is it not a big number? So we have to compare it to numbers, changes in the global mean temperature that have happened before. Right? So we see whether those things change in a big way compared to this. So the last ice age is a good point of connection. The last ice age finished about 20,000 years ago. Most of the UK was glaciated, probably not down to here, but then it was a little further north. But there was enough water taken into the ice to reduce sea level by about 120 meters. In North America, the ice sheets covered the entirety of Canada, all the way down to Long Island and New York City. it was a very different planet, where we have forests and right now we have tundra. The Amazon wasn't a lush rainforest, it was a savanna with little refugia in the middle. It was a very different planet. How much colder was the last ice age compared to today, or compared to the previous one? That's a little bit more of an interaction. So who thinks that it was more than 20 degrees colder? Right? More than 10 degrees colder? A couple of people there, more than 5 degrees colder? Oh, I feel more than 3 degrees colder. Okay, so, and then there's a whole bunch of people who really aren't very sure what I'm talking about. That's okay. The fact of the matter is that the last question is only about 5 degrees colder than the previous one, right? So think about the difference between the time that we had relatively recently and the ice age, just being one ice age, right? That seems like a big deal for a planet, right? One ice age, that seems important. So 1 degree is 1/5 of an ice age. That seems a little bit more substantial, right? Like 1/5 of an ice age is quite a lot. But in the other direction. And we'll get to where we're going in a little bit. So this is not a trivial thing. This is not something that scientists can measure and be happy that they've detected, but actually has no significance. The planet is already very significant what we do. Not just in sea level rise, not just in ice sheets, but also in ecosystems, in heat waves, in rainfall intensity, in all sorts of different things. So how do we put it all together? We put it together using a model. This is an old model. This is a punch card. A couple of you might recognize. Yes, there we go. Something you actually use one of them. This was one line of code. This is before you could type things in, you could type locally, before you had the monitors. Your smartphones are so much more capable than the computer models that we started with. We still use Fortran, which is the language which is this code, which is a little bit surprising to make people who work in computer science. Why don't we just all encode it in JavaScript? And I don't know, I haven't really used the code. But we are still working with models, and I use this picture because it's important to understand that we've been doing this for a while, right? People started off with kind of back in the 1970s, when the first Copernicus mission was in 1956. It really took off in the 1970s. And the reason why we're still doing it now, and we're still using code that we developed from those codes that exist today, is because it works. If it hadn't worked, we would have stopped doing it. The challenge that you have with current model is one that's actually quite nice. You're trying to model something that ranges over 14 orders of magnitude. So for instance, the size of a small particle that seems to cloud is on the order of a micron, 10 to the minus 6. The size of the planet is about 10 to the 8. That's about 18 orders of magnitude that goes from the smallest to the largest scales that you have. Most physical theories, whether it's quantum physics or Newton's laws or general physics, only really span a few orders of magnitude. 14 orders of magnitude is a pretty large chunk of physics. And in time as well, we're looking at things that happen between microseconds and millennia. Again, another 14 orders of magnitude in time. This is a real challenge. If you think about each of those order of magnitude, you chop them up into little boxes. This is a little bit schematic. What you can do with current technology is you can do some part of that model backward. And so if you look at weather models, so the weather models that predicted it was going to snow 6 inches today, which doesn't seem to be quite models go from the global scale down to a few tens of kilometers. And you generally run a climate model, a weather model for a few minutes out to a couple of weeks. Okay? So you have a restricted view of the time scales, and you try and do as much of the spatial scales as you can. And the stuff that we include there, we call it resolved physics. The things that we think that we're doing goes to almost from a priori estimates of the underlying physics. This is a bit that we're relatively complicated. But of course, there's a whole bunch of stuff that's much faster and much smaller that we're not doing now. I must study in my allotted square. So the stuff that's smaller and shorter timescale, what we call subscale processes, that sounds very technical, that just really means the stuff that we have to guess at. We don't like putting that wrong attributes. We do a reasonable job. We try and capture the phenomenology of what's going on in those small scales. But there's a certain degree of empiricalness there, there's a certain degree of ad hocness and arbitrariness. And that makes everybody very, very nervous. Climate models, back in the 1990s, had a greater restriction on the scales they could do, but they went for longer. Things have improved a little bit in the 2010s. Oh, jeez. In the 2010s, the time models got a little better. We expanded out an order of magnitude in time and space. But we still have that same fundamental problem. There are parts of the problem that we can do very well, and there are parts of the problem where we have to make approximations and we have to make educated guesses about what's going on. If you're really uncomfortable with this, you can say, okay, well, since the 1990s and 2010s, and computers are getting faster and faster and faster, right? Why don't we just wait until we can do the whole problem properly? But until then, we won't do it. If you actually calculate how fast computers are increasing in speed, how much we can actually use that, what we're talking about here is about one order of magnitude every 10 years better. And of course, if you want to go out to 2100, we've got another 9 orders of magnitude to go, that means we can't tell you what's going to happen in 2100 until 2100, which would basically put all of us out of job for a while. So we're not going to do that. We're trying to do something that's better than that. So the way that it works is we go out and we measure stuff. We measure things like the reflectivity of sea ice. We measure things like how quickly ice melts and forms as the temperature of the seawater change temperature and salinity. And that's one piece of the jigsaw. We can do the same thing for clouds. We can go and measure how quickly clouds form as a function of their wider environment, how quickly they dissipate, how quickly they rain out, where do they move around, what's the turbulence within a cloud system. And again, that's another piece of the jigsaw. The radiation coming from the sun that comes to the Earth, that gets absorbed by things in the atmosphere, gets reflected from the ground, the radiation that comes from the ground, the infrared, moves up through the atmosphere, gets absorbed by greenhouse gases like water vapor and carbon dioxide. We can do all of those things as well. And again, that's one piece of that jigsaw. And so you can keep on going. You can look at the oceans, you can look at the land surface, you can look at the plants, each one of which has a whole specialty of scientists focused just on that one thing. But then when you put it together, you have something different. You have a picture of the planet and of the climate system that is not complete. You see there's some gaps. But it gives you a picture that actually looks like the system that we understand. And that is what climate science is about. It's the synthesis of all of those some fields that are now subfields, and the people who are experts don't think of themselves as being subfields of climate science. Meteorologists still consider themselves a meteorologist, as an oceanographer. But really, they're looking at certain aspects of that whole climate system. And the climate science part is pulling all of that together so that we can look at that system as a whole, not just in pieces. What do you get when that happens? You get simulations like this. This is a simulation from Goddard Space Flight Center, where I work. And what you're seeing here is a simulation of a single year, and all of the different colors are particles in the air. Right? So the orange are dust particles, mostly coming from the Sahara. The blue is sea salt particles that are kind of whipped up by the winds over the ocean. The white riskiness is sulfate pollution that comes from the burning of sulfurous coal. And you can see, particularly over China, that's a big issue there. And obviously this is a simulation of the situation 10 years ago. It's actually much worse now. The green colours are associated with carbon, organic carbon, that comes from biomass burning. Each of those red dots is a fire, and from each fire there is a lot of stuff that's coming out, smoke and particles. You can see in this simulation that there are large-scale patterns, just as we saw in the first simulation when we started. You can see these large-scale patterns of aerosols and clouds all kind of interacting. So around the Antarctic continent, you can see these patterns of storms taking the salts and moving it around. And you can see that all of these particles are being affected by the weather of the climate. But they also affect the weather of the climate because they have an interaction with radiation. And if you saw carefully, there was a volcano that just went off in Madagascar. A volcano produces sulfur dioxide, and so that's what you're seeing that white riskiness dissipating. The complexity of these models rivals the complexity of the real world. It's less complex, obviously. But the patterns that you see, the emergent patterns that you see, are real and well matched to what actually gets observed. If this was the only thing that we were trying to do, it would be a huge, huge challenge, and we would be doing quite well. Right? I would be able to produce these simulations. I would be able to predict the weather, at least for a few days, and it would be impressive. And we would be able to take our hats off and say, "Oh yes, well done, clients." But we want more. We want more because we know that system that we're just modeling can be kicked. It can be perturbed, it can be changed, because we know about that history of climate change that we've had from the observations going back many millions, if not billions of years. So what can kick the system? What causes the climate to change? What causes any of this to vary? So one of the first things that people note is that the Earth's orbit wobbles. And it turns out that it wobbles on a relatively slow timescale, tens of thousands, hundreds of thousands of years. And that, in fact, can cause ice ages to come and go, including the last ice age 20,000 years ago. So wobbles in the Earth's orbit have a very clear impact on the sky. Changes in the sun becomes brighter and dimmer on linear timescales over the length of the history of the world. The sun has brightened by about 30%. And of course, by the end of the world, it will be brightened much more. It will be a red giant, and we will be toast. But that's not for a while, so not an immediate policy problem. Volcanoes have a big impact on climate. They put enough stuff into the atmosphere, a lot of it is reflective and actually keeps the sunlight from getting to the surface and cools them. I'll give you an example of that in a second. Smoke, biomass burning. If you can see something in the air, then it is impacting the climate. The ozone layer. that changes the climate, changes the temperatures, it changes the winds around the South Pole. So the winds have increased by about 30% in strength around the South Pole in the last 30 or 40 years. Deforestation changes the climate by changing the texture of the land, how much sunlight is reflected, how water gets cycled, and we are deforesting the planet at a not quite ever-increasing rate, but at a pretty rapid rate. And of course, contrails, these change the climate. They're not by very much, but they're one of the aspects of our activities that impact the climate. But they're not the biggest. The biggest is carbon dioxide and greenhouse gases. And I'll explain why I do that in a second. So lots of things can keep the system. Right? Now, for us to have any confidence that these models are useful, we have to test them. It's not sufficient to just say, the models are really, really complicated, and look at the nice patterns I just showed you. That is not sufficient to demonstrate they're actually useful at predicting something we need to know. You have to test them. So what we talk about when we talk about testing climate models is the notion of skill. Right? A model is skillful if it does a better job of predicting something than you'd have done just by guessing, effectively. Weather models are skillful because they do a better job of predicting weather than you would be able to predict just from assuming persistence. The weather today was the same as tomorrow. Weather models are skillful out to about 5 to 10 days, depending on where you are. But they're not going to get much more skillful than that because of the chaotic dynamics of the climate. And so weather models are never going to be skillful beyond 2. But they are increasingly skillful at 3, 5, and 10 days. We can do that same test for climate models, but we have to compare it to slightly different things. So here we go, here's an example. So we have had big volcanoes in the relatively recent past. The one I'm going to talk about happened in 1991. There was a volcano in the Philippines. And what happened is that it erupted in June 1991. And it put what we call aerosols, these small particles, into the stratosphere, above water clouds, above the water, and it put a huge amount of stuff in the stratosphere. And then it spread out, and it stayed there, it stayed there for about 2 or 3, 4 years, right? It kind of slowly decayed. Because these particles are reflective, that means that as the sunlight comes in, they're more reflected out to space. And so the amount of energy that got to the surface decreased by about 3 watts per meter squared. Now, 3 watts per meter squared, 1 watt is a Christmas tree bulb, roughly. It's old school Christmas tree bulbs. And 1 watt per meter squared is one of those in a meter squared. But that's actually quite a lot of energy once you average it over the whole globe, 24 hours a day, 7 days a week, 365 days a year. So this is a big perturbation into the system. And you can see that that change to what we call the radiation balance lasted for about 2 or 3 years. So if you're having less energy going into the system, one might naively say, oh well, the planet is going to get colder. But how much colder is the planet going to get? And do we understand the factors that control how warm or how cold it gets for a change in radiation? The answer is yes, we do. We do manage to do that. So here is both the observations of what happened and the model estimates of what should have happened. And you can see they line up quite nicely. In fact, our group in October 1991, this is 3 months after the eruption had gone off, did some simulations and published a paper that predicted what was going to happen before it actually happened. They said, well, the maximum cooling is going to be about half a degree C, and the cooling is going to last about 2 to 3 years. And that's exactly what happened. And that was a prediction from a climate model that's now a pretty old school climate model, but that was a prediction of things that happened before they actually did. Which, that's a pretty good prediction. But you can do more. You can go back and you can say, well, not everywhere gets cold at the same time. Some places get warm and other places get cold. It's because of how the winds change. And it turns out that if you look at the top picture there, the observed temperature changes after a big volcano are such that in the winter time across Europe, it actually gets warmer. Despite the fact that the whole planet is getting colder, in Europe it gets warmer. And that turns out to be because the winds across the Atlantic speed up and they are more effective at bringing warm ocean air onto the cold continent, thus producing a winter warming effect. And the models do that as well. And so we can take one of these natural experiments and test all sorts of things. The radiation change, the surface feedbacks, the dynamical feedbacks, the consequences of the dynamical feedback. And we can go tick, 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 tick. Yes, the models do a skillful job. They do better than you've been able to predict just like that. Stimuli thinking. We can also ask, well, what's been happening over the 20th century, right? So this is a model and an observation, slightly smooth so that it doesn't get too noisy. What you're seeing here, the blues and the yellows, is weather, right? Weather is not correlated in the models and the observations because weather can't be predicted years and years in advance. But as you get towards the end of the century, you're seeing a new pattern. Something that isn't just the weather, something that in fact is a signature of climate change. And you see that both in the model and in the observations. And so the model has a skillful approximation of what actually happened in the world. Now we can go further. We can ask ourselves what in the model caused that pattern to emerge and what didn't. Okay? So, what is really what we do? This is an interactive graphic that we did in Bloomberg Graphics. You can Google it if you want. And so what we did is we took that temperature curve and we asked, of all the things that might be changing over the 20th century, we looked at the orbit, we looked at the solar forcing, we looked at volcanoes. Those are all natural things that are just going on. And we can add them together and say, well, what would be the natural impact on climate? You know, if that was the only thing going on. And you can see there, it didn't match up to what the actual observations were. But we're doing things. We're chopping down forests. We're creating ozone pollution. Those two things don't really make that much difference. We're creating air pollution, aerosol pollution. That actually is cooling the climate. But if you actually look at the effect of greenhouse gases, it's warming the climate more than we actually saw. You combine all of the human effects together, and what you find is that the large-scale trends are actually pretty well captured. You combine again the human effects and the natural effects, and what you end up with is a really good match to what actually happened. And it's this kind of fingerprinting that allows us to say with some high confidence that the trends that we're seeing over the last 50 years, 60 years, are almost entirely due to our efforts. Yeah. We can go back further. And one of the things that we can do is we can start to really use the complexity of the paleoclimate graphic. For instance, a lake burst in northern Canada 8,000 years ago. This was a lake that was larger than any of the Great Lakes now. The total amount of water in this lake was about ½ a meter of equivalent sea level rise when it was spread around the whole globe. That's a lot of water. And what was happening is that those ice sheets that were remnants of the last ice age were slowly disintegrating. And at some point, all of that water spilled into Hudson Bay and into the Labrador Sea. At the same time that that happened, there was this big cooling spike that we can see recorded in Greenland ice cores and in lakes in Germany and in bogs in Newfoundland and in ocean sediment cores off the coast of Norway. Our ability to model that gives us a test of those complex models that include the oceans and include the isotopes, and include the dust, and include the other aerosols. And we can make a one-to-one match of all the different things that were measured 8,000 years ago, but are measured today, but they were back 8,000 years ago, and show that the models that we designed for today go back in time and produce skillful predictions of what you should have seen in the old records. And the funny thing is that those are the same tests that we need to build probability in things like what the methane feedback is going to be as the planet warms, which is something people worry about. We can calibrate that against what the methane change was 8,000 years ago. We can also look at the different things that we're doing with aerosols and methane and ozone and smog, and produce air quality statistics and test those against air quality changes that we're seeing around the world with the same models and with the same machinery. So we can take all of those things and we synthesize the modern data, we synthesize the paleo data, we synthesize the physics and the observations and the paleoclimate record to produce models that are skillful across a whole suite of different questions. Now, I mentioned the future. This is a good thing. And this is why I'm bringing it. If we had observations of the future, we obviously would trust them more than models. Right? But unfortunately, observations of the future are not available at this time. And that is obviously always going to be true. So if we're going to make a prediction, we need models. How have our predictions worked out? That's a valid question. This is a set of model runs that were done in 2004. And they used information up to about the year 2000 in terms of what was going on with greenhouse gases and the sun and things like that. And they predicted things going forward. So what I've done here is I've plotted the envelope of all of their predictions. And that envelope is made up of two things: the weather, which isn't predictable, and the uncertainty in how sensitive the climate is affected. And so, as you can see, that is a pretty broad band in the high-pass period when we know what the answer is, and it's slightly broadens out as you go towards the future. And the colored lines are different estimates of the actual change in the global mean temperature. And you can see 2016 is the mark there as an estimate. And you can see that we're pretty well. We're actually, the mean trend of these models is actually pretty close to the mean trend in the real world. And that's after basically about 15 to 16 years of real prediction. So they're not doing too bad. What does that look like going forward, going further forward? Now there we have a little bit more of a problem, because there we have different scenarios that are possible. We have different choices that society and history are going to make. We can do something that we can describe as aggressive mitigation. That would be equivalent to reducing emissions very quickly, about 80% by about 2030. This is otherwise known as the completely impossible scenario. But that keeps us at an average temperature of less than 2 degrees above pre-industrial by the end of that, by the end of the century. Or we can decide not to do anything, and we can decide to burn all the carbon that we can find. We can burn all the coal, we can burn all the oil, we find the methane hydrates, we burn that, the tar sands, we burn that, the oil shale, we burn that, the natural gas, we burn everything. The peat, we burn that. And then you end up in a situation that is very red. Now, I chose the color bar, so it's not a total coincidence. But those red saturated tones that you're seeing here are 4 degrees above where we are now. So if you remember, we've gone up 1, plus 4, that's 5. That's an ice age unit in the other direction. So if we think that the Ice Age was a very different planet, and it was, where we're headed under a business as usual scenario is also a very different planet. And a very different planet in ways that we can't fully predict. The one at the top is the medium scenario. That's the one that assumes that we're doing our best, but our best is not quite good enough, and the temperatures rise by about 3.5 degrees by the end of the century. This is still a big change. This is a planet that doesn't have any sea ice in the summertime in the Arctic. This is a planet that has significantly more intense rainfall. This is a planet that has big changes in where it rains and how broad the arid areas in the subtropics have become. This is a world where temperatures in the tropics are outside of any historical norms. All the time. That was a serious change too. And so on to impacts. I'm contractually obliged to include a picture of polar bear before that. Not because I like polar bears particularly, but I could take this picture. That is a polar bear that likes me a lot. Basically, it hasn't fed for about 6 months while there was no sea ice in Hudson Bay, and was looking at me as if I was there. It was not quite as close as that seemed. It was like that far. They're very cute, but do not love the bear, respect the bear. But the issue is not polar bears, though they are in trouble. The issue is much more likely to be a creature like this. Anybody know what that is? It's a mountain pine bark beetle. A totally uninteresting species to my mind, though presumably some entomologists think it fascinating. But it has this curious phenomena that during the winter time, it has about a 6 to 8 week window as it prepares for the winter. And what it does, it produces antifreeze so that it can last through the harsh mountain winters in Colorado and Alaska and British Columbia. If during that 8 week period it gets cold enough, minus 20 or so for a few nights, that will be the end of that pine bark. Because it hasn't yet prepared enough antifreeze to last that. And that is what would happen year on, year out, to limit the number of beetles that there were. But it turns out that has not been happening as much. And it's taking a lot longer for those cold temperatures to arrive, if they arrive at all. And so far more beetles are surviving the winter. And then in the spring, far more larvae are coming out, and far more trees are being destroyed. And if you ever go to British Columbia or the Rockies, you see huge swaths of forest that have turned into just brown trees as far as the eye can see. And all of that is due to that tiny little critter that just happens to have a small temperature-dependent window for survival. That is not something that's easy to predict. And I don't know what the next species is going to be that has a particularly special climate response. So what is climate science good for? Knowing where we came from. Knowing what our species, our planet, and our ecosystems have lived through before. That's very important. Working out why that happened. We can work out what's happened over the 20th century with pretty good confidence. We can work out what's happened over the last millennia with slightly less confidence. Going back over the last 2.5 million years, we have some good ideas about why climate change. But going back through the Cenozoic, 65 million years, there are some mysteries, but there are also some really insightful pieces of work that tell us why the climate in the Eocene was so much warmer than the climate now. It may come as no surprise that a big part of that is also carbon dioxide. Climate science is the only tool we have that allows us to estimate where we may be going. And without that, we don't know what to prepare for. We don't know what to mitigate effects, and we don't know how to adapt. Climate science helps us assess our vulnerabilities to climate change and to climate changing, and what the risks will be if that starts to change in our people, which it actually already has started. But, and this is kind of the heart of why I'm here and I'm talking to you. This is a quote from Sherwood Rowland, who is the Nobel Prize winner for discovering the science behind ozone depletion. He said, "What's the use of having developed a science well enough to make predictions if, in the end, all we're willing to do is sit around and wait for it to happen?" And that encapsulates our dilemma as climate scientists. I have two hats. One of which says, I predicted that 2016 was going to be a record warm year back in March. And I'm thinking, oh, it was a record warm year, but it's very lucky to get it. And I'm thinking, oh, yes, how clever. And then my hat as a citizen, and as a person, and as a father, is, oh, that's another year of record warm temperatures. And that's another year where it's clear that we actually are on the trajectory that climate science has warned us about for the last 30 years. And that's not good news. But the converse is, we are forewarned. The science allows us to make predictions so that we can avoid making it come true. We avoided a huge problem with the ozone hole because we took action to reduce CFCs and other ozone-depleting substances before it became as bad as it could be. We are reducing emissions. We are reducing emissions by better efficiency, by increasing renewable standards, by reducing the use of coal, by driving less, by being more efficient, by insulating our houses better. We are reducing emissions. We're not doing it fast enough for that aggressive mitigation possible. But we still have choices, and we still will always have choices. There is never going to be a point where we're going to get to a decision, and it isn't going to matter what our decision is. Whatever happens, we will still have choices to do something that is better for the climate or something that is worse. And we need to get better at making those decisions. Right? Because right now we're making those decisions on infrastructure, on pipelines, on grids, on electricity production. These are decisions that are building in emissions or lack of emissions for decades to come. We are smart. I look at young people here at university, I look at younger people, like brothers think about it, and they are smart. Okay, I have a little bit of trouble with upstairs. But they're smart. And we can do better. Right? When people started burning coal, they didn't know that this was going to be a problem. They didn't know that that was, by an accident of history and chemistry, that carbon dioxide was going to be such a dominant change and a dominant factor in the 20th century. But now we do know, and that changes the moral calculus. And that should empower us to fight to make better decisions and for other decision makers make better decisions, and for us to make better decisions. And so while I'm disappointed that my predictions come true, I'm also emboldened to let people know that there is still good decisions to be made and better decisions to be made in the future. So that is what kind of science is. Thank you very much.
Thanks, Gavin. Okay, so we do have some time for some questions. I can only see it. We have people with roaming microphones, so if you can just hold your question until somebody gets to you. So do remember we are on live streaming this evening for some motivational for people at home. So, yes, please.
Thank you very much for a fascinating introduction. My question is this: in 8 days' time, we'll have a president of the United States who does not believe what you just told us. How worried should we be about that?
So before we started, we made a little side bet that the first question would be about Trump and hasn't been. So let me be a little diplomatic. I'm a federal civil servant. I work for the executive branch, and the executive branch does what is told by Congress. And that's how it has to. What the executive branch does via NASA is extremely comprehensive and very, very complicated, and provides input to weather forecasting models, to natural hazard planning, to emergency services, and as well to climate change. We, I think, will, if asked, stress how important NASA's role is across a whole swath of different topics. And
We have a question right here at the front, and then there's one at the back. So the microphone is coming here. So feel free to put your hand up, and I'll try and remember and make sure that it's all please.
Good evening, and well done, thank you very much. My name is Graham Rabbits, and I must declare a couple of interests first. I used to be the Environment Manager for Associated British Ports, which handles 25% of the UK's trade. I took that job on as the European Union were introducing the environmental legislation, which had a huge, the ports have a huge environmental footprint, so very interesting. And in the 10 years before that, I was Business Development Manager and involved in negotiations in Seven Barrows. So I think I've got a little bit of experience. Indeed, I might be the oldest person in this room. And I think I know where quite a lot of the potholes are because I've fallen into most of them at one time or another. But I think the problem that the scientific community has is that the public, and I'm probably nearer to the public than the scientific community in some senses, sees the scientific community as homogenous. And they don't distinguish between, if you like, the purely scientific community, where there is true scientific integrity. And that is a task that you must address, is to lift yourself out of the mire, I think, because the other parts of the scientific community are the part that you're slightly involved in to some extent, and that is the political scientific community, where in fact what you do can be politically driven. And it's very, very difficult, I find it hard to see how you're going to get out of this, and where the decision making also, there's sometimes not a very good quality, it's yes minister quality, and that's not good enough for this task. The other problem is, in this country particularly, is we've got the NGOs, which are often single issue, and some, like RSPB for example, have huge funds. In fact, they have more members than they had until quite recently, more members than all the political parties in this country have together. Huge authority, I work with them. successfully for many occasions. But I hope that what's going to happen over the next period is that you can actually bring out the distinction between these three elements of the scientific community. The NGOs do a very, very good single issue job, but they sometimes use their lobbying power to an extent that is not wholly justified. That's been my experience over that long period. So I beg you to try and see if you can bring out that lobbying difference between those three segments of the scientific community.
Sure. I'm not sure what the question is.
Paraphrase.
Yes.
Where is the line between science and advocacy? Should there be a line? Your predecessor, Jim Hansen, famously moved between policy and science.
Right.
So is that what
No, so beyond that is not. I mean, anybody that does science is also a citizen. The idea that science only proceeds because every single scientist is a noble, objective searcher after truth is a mythology. Right? None of those ideal scientists exist. Science proceeds because imperfect, subjective, driven people with huge egos push things out, and the stuff that survives, the stuff that gets replicated, the stuff that has predictive value, the stuff that's useful, makes it into the textbooks and seeds the next generation of scientists, all of whom are also imperfect, subjective rules of emotions and I'm here, I'm performing, right? If I told you that I didn't have a little bit of fun doing this, you wouldn't believe it. So am I doing this because I'm having a little bit of fun, talking to people and trying to get them to understand what we do? Or should I just pretend that I'm an automator, English, not English major, this is just some automatic thing. No, it's not. I speak in public because I do advocate, and I don't shy away from that. I advocate for a better class of conversation. I want people, when they argue on the basis of their different values and their different priorities, I want them to have an argument that's rooted in reality instead of nonsense. I don't apologize for my advocacy. Other people find other things to advocate for, whether it's education or greater science funding or to save the world. All of those things are worthwhile, and people should own the advocacy that they do. And the RSPB advocates for birds, as they see it, okay, and they should. And they make no pretense about it. I don't control. I would hope that when they do lobby, they do advocate, that they root their advocacy in the science combined with their values, right? And people are imperfect, and so occasionally you will find that people get the wrong end of the stick. And sometimes people go too far, and they will be corrected because that's the nature of our political process, right? But it's expecting everybody to be perfect all the time is expected to happen, right? What we expect is that when people go too far, we have people corrected, and that in the end we end up somewhere that's rooted in the science, appropriate.
Question again, please?
I've got two questions. One regarding and kind of the impact of environmental impact has on climate change and whether that's actually included in the real factors when it comes to climate science. Is it actually looked at how much of an impact it has on climate change? The second one is what we can do by this problem, because yes, we can all look at the new development goals and kind of campaign for our government to implement the policies and do more about things, but what can we on ground citizens actually do? more alluding to a specific thing here. Agriculture is one of the big problems when it comes to CO2 and greenhouse gases, and the impact on the trials on climate change. So some of us might be environmental activists, some of us might follow mandates. You're talking about 300, 400 people here. What can you tell us to do? What can we change in our lifestyle? Because a lot of this stuff, when we talk about the impact, a lot of it, deforestation and everything, most of the stuff that's happening is to supply the first world with the needs and the commodities that they want, not necessarily require. So what can we, as citizens,
so let me break that down into three questions. One, what's the impact of water? No scale war doesn't actually, it has a local impact, obviously, often cities are living story times when it's had a very large environmental impact are times, for instance, during the first Gulf War, when the oil fields were set afire, and there was a huge amount of oil that was burning, lots of black smoke. People estimated the impacts of that black smoke, both on air quality in the region and it was pretty small. Locally it was a very big deal, but in a global sense it was not good. People are obviously worried about the environmental impacts of much larger scale wars, like even a nuclear revenge. And the best estimates of that now are, yes, first of all, it's a nuclear war, so that's not a good thing. But then there would be very severe environmental changes after that as well, also not a good thing. So let us avoid nuclear cancer. I don't feel bad advocating for no nuclear. And then your second question was like, what can you do? And then like the specific thing about how do you get impact agricultural choices. So what we can do is we have to recognise that we exist in multiple worlds. We're individual consumers, so we can make choices about our individual consumption. Sometimes that's hard to make a big difference there because it's a small thing compared to the vast bulk of the other 7 billion people. But we're also members of our community. Right? We're members of our town, our city, our county, our country, our region. And at each of those levels, there are people making decisions that have environmental impact. If it's your church, right? They're thinking about replacing the roof. Well, how are they going to do that? What can they do there that would make it more efficient? What can they do there to make it the schools that your children go to, or your parents go to? They are big users of electricity, big users of environmental. They have relatively large environmental footprints. How can they be helped to have smaller footprints and more efficient? So you can do all this. If you go up level, on the national level, you have a vote, you have the ability to campaign, you have the ability to write letters, you have the ability to try and make sure that the people who are making decisions get the problem that you as you see. With the specific issue of agriculture, there are obviously aspects of present-day industrial agriculture that, in my opinion, are not good for the animals, the countryside, or the people who use it. And I think it's certainly within your power to eat better and to avoid industrially processed meats, for instance. They have very high carbon food and I don't generally advocate for this, but I even make decisions along those lines as well. And I don't eat industrial meat as much as I can. And that helps a little bit. It sends signals, it reduces the demand for these things, which in the end it reduces for I think it's really good. That's a hard sell to a lot of people for obvious reasons.
You have a question? You're shaking your head.
No, because mine's already been asked.
Okay, then we have one right at the back on the far side, and a gentleman in the middle, and just you. Yes, one, two, three.
Do you think the British university educational system needs to be changed to be more like the American one, so that students in science can have a wider range of studies, with the aim that they'd be better able to communicate with the public if they studied humanities as well, to improve scientific communication, to captivate the public with a good narrative?
I sense that might be a slightly delicate question. So I did my undergraduate here, I read maths at Oxford, and I only ever did math courses, so I never took a liberal arts course since I was 16. But you have to think of your education as being more than just what people are trying to teach you. Education is what you end up with after people have tried to teach you things, and after you have explored everything you want to explore and continue to explore. I read a lot of history. I read a lot of political science. I read a lot of science. And I learn a lot from all of those things, regardless and despite the fact that I didn't have a formal education. Is it a good idea to allow people to have broader formal education? I look at the situation in the US where there's a lot of people that go through 4 years of college, and in the end, all they've done is like the intro courses of 1,000 different disciplines, and they end up with a very rather unspecified degree in something. The benefits here is that if you make it through something you end up with something with actual skills. And knowledge. When we hire graduate students, there's a big difference between graduate students from the UK and Europe and graduate students from the US. You have to, I don't need to teach graduate students from Europe how to do integrals and differential equations and process data. Not so much. But, I've hired graduate students in the US who were English majors, but who were inspired by the science to go back to school and do science courses, and actually some of my best graduate students weren't science majors at all, right? And yet have made very useful contributions to the field, and then have gone on to do things that are mixes of, policy and science. And so, it's tempting to say, oh, it's just change the system, everything goes better. For an individual, you can make any of these systems work for you by being smart about your choices and smart in your reading, smart in who you hang out with, what you do. Knowing what's best for society as a whole, that's a much trickier. It's a much trickier thing. I don't think there are easy answers to that.
We had a question, so before you do ask this question, no pressure, but you are stopping us drinking all the free wine. Which has been served. So I'm very mindful, so I'm going to get on. I'm going to do this. The questions. Quite short, sir.
No, you can squeeze in a couple more if they're smart.
The institutional sector about McDonald's, you mentioned
that obviously the scale may be varying. You've also said that they improve over time, so it's been improving. How much more do you think they need to improve for these skepticism to go away? Do we need to make more practically better, or can we go along and talk about the work?
So that's a great question. So it depends entirely upon what that skepticism is based. If that skepticism is knowledge-based and they're actually trying to predict something and they just don't see that the models have enough skill to usefully predict it, then as the models get better, that skepticism will go away. If their skepticism is rooted in a total abhorrence of what they perceive to be the policy consequences of everything that we're doing, it isn't going to change. And so there are both of those things, right? And you have to be a little careful about, where those people are coming from, and what they're actually skeptical about. Because there's no point in telling somebody about your new violation of tropical connection if they think that all of this stuff is being driven by a vegetarian socialist agenda from Belarus.
Okay, yes? Yes, please.
Thank you for the lecture. I have two questions. Quite short. The first one is obviously climate change is a global problem, so it requires international cooperation. I'm also wondering what does the future look like in getting a country like getting a global movement forward to actually introduce meaningful legislation on a general basis. And the second question is, how can we rely on alternative renewable energy sources in order to combat aggressive climate change?
Okay, so we've got two things. They're kind of connected, so I'm not asking you one. Yes, this is a global problem. Carbon dioxide emitted in China or in Australia or in the UK has exactly the same impact on the planet. And so if we reduce emissions here and reduce them over there, we can't really get very much. And so international cooperation on this is absolutely key. But thankfully, we actually have got a Paris Agreement which 192 countries have signed, and 90 of them have ratified, so it's going into force. So that does exist. Now, the estimates of what people have pledged under Paris compared to what we need to be doing, they fall short. But there's no other, this is a totally unique agreement. There's no other agreement in the world that has symmetries with actual action associated with it. And so what is going to happen, hopefully, is that people are going to do what they said they were going to do, which for the most part are a little bit of low-hanging fruit. And people will get better at doing what they think they're going to do. And you will learn from the other countries and other initiatives that are going on, and hopefully spread the best practices so that we can make a bigger dent in the next shock of emission reductions that we need to be making in order to avoid some of the worst. Does moving to renewables help us avoid those worst impacts? The answer is yes. But there are obviously issues with renewables. One of them is intermittency. One of them is building grids that are large enough and smart enough to be able to integrate enough intermittent sources. But we're making a lot of progress on that. And while there's a lot of people that say, oh, it doesn't work, it doesn't work, it doesn't work, they really should get out of the way of the people who are actually making it work. Is it going to be enough? Is it going to be enough fast enough? Immensely.
And we have a question, and I think one of you asked.
Hi, I was just wondering, as well as reducing greenhouse gas emissions, do you think geoengineering will have a future? And if so, what types of geoengineering do you see suitable for the future?
Oh, that's a great question. So geoengineering, for those who aren't aware, are large-scale interventions in the climate of deliberate, as opposed to kind of accidental modifications that kind of lead to that. So there's two classes of geoengineering. One is let's find something that cools the planet to counteract the warming from the carbon dioxide that we're increasing. And then there's another kind of geoengineering which is basically sucking the carbon dioxide out of the atmosphere and burying it in somewhere to kind of counteract the emissions from everything else. Both of those are physically possible. People have costed out what it would take to put in a Pinatubo every year, which is pretty much what we would need to counteract what we're doing right now. If we did that, but we still continue to increase the carbon dioxide, by the end of the century, we have to be doing 2 or 3 Pinatubos every year. But then the tricky thing is that we wouldn't ever be able to stop it. Because if you stopped, you saw how quickly the aerosols come out of the stratosphere. It's about 2 or 3 years. In that 2 or 3 years, you would have a climate change so large that it would dwarf any geological events, with the possible exception of the Cretaceous and extinction events that are huge meteorology. Okay? So you don't want to do it. The problem with geoengineering, though, that's sort it's not the physics. The physics is actually pretty well. The mechanism by which we can do it is not beyond a large country. But the geopolitics of geoengineering are why it won't happen. Think of a scenario where the US wants to do something. They have to go through an environmental impact assessment, and there's going to be call out legislation to go with that. The same we truly think European. And so you're left with countries that are kind of slightly looser environmental regulations. Say Russia. Now Russia doesn't want to do it because Russia actually thinks that warming the Arctic is going to be good for them. So never. China is actually very vulnerable to rising sea level. Anybody who's been to Shanghai is at this Tianjin is very much less. Even Beijing is actually not that high above sea level. It's not inconceivable that the Chinese could decide. So why we're not going to wait for you guys? You don't have to do environmental impact assessments. And they just go ahead. I mean, they're producing far more sulfates locally now than would be needed to put into the stratosphere. But one of the impacts that we get because of this change in the stratosphere is it doesn't quite cancel out carbon dioxide. It's not anything. And so a world that is warmed by carbon dioxide and cooled by geoengineering has less rainfall than a world that's actually. And in particular, it has less rainfall controls. And so countries, for instance, India, that are very sensitive to monsoon are going to get very anxious. And the first time something happens to the monsoon, whether or not it's actually connected to anything the Chinese are doing, will cause a very serious geopolitical incident. And both of these states are nuclear armed. What's going to happen? Right? It's not going to be pretty. And so the things that are going to prevent us from doing geoengineering are not physical, they're not scientific, but they're going to be legal, ethical, and political. And so I'm pretty confident that will not happen. Now, the other kind of geoengineering is sucking carbon dioxide out of the air. There's a number of techniques that you can do that. That's 9 in terms of changing the climate. Just put it up, plug one place and draw it very more. The only problem is it's extremely expensive. And so the cost of doing that, to suck carbon dioxide at the same rate that we're putting it in to stabilize concentrations, is far more than the cost it would be to not do the emissions in the first place. So unless there's a huge technological breakthrough, that's a non-starter. But they're interesting to me.
Again, I just need to recap that there is refreshments outside, some of them out on the bench, so please do have a conversation amongst yourselves, come and speak together, bring your questions outside. I hope now you are all convinced that climate science is about something.